Okay, so everybody who have joined the class, I hope you are able to hear me. If yes, make sure your video is on. We're going to start the class now. Everybody who has joined the class, please make sure your video is on. We're going to start the class. And if I'm right, today we are going to continue from where we left in the previous class of nuclei. I hope most of you were there in the previous class where I taught you nuclei, isn't it? Anybody is there who was not there?
I was
In the
not.
previous. Okay.
Sir, I was also not.
Okay. So those who are not there, I think you have not got the link also for the class. So you have not seen the previous class video also. It may be a bit difficult for you to understand today's class, but I'll try to keep it as simple as possible. Remind me after the class gets over, I'll share the link with you. You can see the video. Okay. And learn whatever you missed in the previous class. Okay. Fine, Kirti. I hope you're fine. Okay. So let us start today's class. And today we are going to continue from where we left in the previous class. In the previous class, we started learning about nuclei. I'll just recall in short whatever I have taught in the previous class, where I have talked about, first thing which I started talking about was, what is a nucleus? It is a central part of the atom, which is positively charged. Most of the mass and the charge of the atom is concentrated here. Positive charge, I mean. So whole positive charge and most of the mass of the atom is located where? Is located at the center of the atom, which is called as a nucleus. So nucleus contains neutrons and protons. Together they are called as nucleons. So nucleons means family of nucleus. Who are the family of nucleus? Neutrons and protons. Then we learned about how a nucleus is stable. That is, if we have only positive charge inside the nucleus and we have neutrons inside the nucleus, neutron is definitely neutral. If there is neutral charge, like neutral particles present and positive charge present, all the positive charge are trying to repel each other, then how come the stability of a nucleus exists? We spoke about that and we spoke in terms of nuclear force. I said you, there is something called as nuclear force, which is attractive force for a very short range, 0.8 to 2 Fermis. That is, if two nucleons are present in the range of 0.8 Fermi to 2 Fermi, they will have a very strong attraction. Strong means very strong. It is the strongest force in nature. Strong nuclear force. That nuclear force is charge independent. It means every nucleons have this force of attraction, whether it is proton-proton, proton-neutron, neutron-proton, or neutron-neutron. All the particles inside the nucleus, every two particles inside the nucleus are going to have attractive force, which is called as strong nuclear force. And this strong nuclear force is binding the nucleus. Remember that. Because, as I said before some time, even if you have the positive charge repelling each other, man, this is not for 10th. It's for 12th. Today you don't have class. Today you have test only. Not today, that is tomorrow. Check properly. It was for tomorrow. If you want, you can go to the main building. First floor, Sari sir is there. You can speak to him. Okay? Thank you. Yeah. Coming back, sorry. So I was talking about the nuclear force. So I said that inside the nucleus, there are so many positive charged particles. If suppose we have 10 protons and 10 neutrons, these 10 protons are repelling each other, right? So we have strong repulsive force. But all the 20 nucleons, that is 10 protons and 10 neutrons, they are attracting each other with what force? Strong nuclear force. Since this strong nuclear force is much, much larger compared to the electrostatic repulsive force, the nucleus is able to be stable. That is, it is not bursting out and it is stable. And one more thing is there. I told that if two nucleons are too close, below 0.8 Fermi, then the force becomes repulsive. That is, the nuclear force becomes repulsive. And if it is beyond 2 Fermi, then nuclear force becomes 0. One graph also we have drawn. If you remember, that graph, let me just draw it here for you. By the way, give me a second. No? So if I draw the graph of the nuclear force versus distance, something like this the graph was, if you see the NCERT book also, something like this, almost becoming zero. So this graph very clearly tells that only from around 0.8 Fermi to 2 Fermi, we will have a attractive force between the nucleons. Beyond 2 Fermi, the force will become zero. If the force becomes zero, then the nucleus loses its stability. That's why all the nucleus, which are big nucleus means it has more amount of nucleons, they are unstable. Why they are unstable? Because since nuclear force is very short range force, if the nucleus becomes big, the charged particles becomes far from each other, the attractive force between them reduces and electrostatic repulsive force starts dominating, and that is why we are going to have instability of bigger nucleus, and that justifies why uranium, plutonium, lanthanides, actinides are less stable. They are radioactive, they disintegrate easily. We'll learn about this in more detail today. And one more thing which I stressed in the yesterday's class was something about binding energy. Very important topic. You can expect the question to come for sure from this topic, which is about binding energy. So we were talking about binding energy, and if I am right, I would have given some definition of binding energy also to you. I should have told you binding energy is the energy which the nucleus is short of before becoming independent. That is in order to become independent. So what I said, if you have nucleons, suppose you have 10 protons and 10 neutrons, they may have some mass. Let the mass be some 20 units. 20 protons have 10 protons have 10 units mass, 10 neutrons have 10 units mass. Together they have 20 unit mass. When they are brought together, that is when the nucleus forms, when the protons and neutrons are assembled together inside nucleus, these mass does not remain 20 now. It becomes 17 or 16 or 50. So there is some mass defect. What is the meaning of mass defect? It is the mass which is lost when a nucleus is formed. It means whenever a nucleus is forming, there is some loss of mass, and that loss of mass is called as mass defect. Now, how it takes place? It takes place, suppose, if you have, as I said, if you have 10 protons and you have 10 neutrons, and independent mass, let us assume it to be 20, 10 plus 10 is 20. When we combine them, we observed by using mass spectroscopy experiments that the net mass now is not 20, which was expected. It is now less than 20. And whatever mass the nucleus is short of, that mass only is responsible for creating binding energy. Because as per Einstein, if you multiply mass with square of speed of light, you get energy. And that energy only is binding the nucleus. I even gave the formula of binding energy to you in the previous class. Amruta, your video is off. You want to be in waiting room? So I said binding energy is equal to ZMP plus A minus Z into Mn minus M of nucleus. If you remember this formula I gave in the previous class. It's a very simple basic formula. What it says that, see, Z means what? Those who are not in the previous class, Z is atomic number. What is A? Mass number. So if you subtract, what is the meaning of atomic number, by the way? Atomic number means number of protons. What is mass number? Number of neutrons plus protons. If you subtract A minus Z, what do you get? You get number of neutrons, isn't it? So if I multiply number of protons with mass of each proton, and if I multiply number of neutrons with mass of each neutron, I get the total expected mass of the nucleus. This whole thing is expected mass of nucleus. Expected mass. And this mass of nucleus is found by using mass spectroscopy experiment. So if you subtract these two values, then you get binding energy of the nucleus. Because this, not binding energy, this is called as mass defect, sorry. This is mass defect, delta M. When you multiply this delta M with C square, then you get binding energy. And if you want to find binding energy of each nucleon, what is the meaning of that? BEN means binding energy divided by total number of nucleons, right? That will be obviously A. That will become equal to delta M into C square by A. This is the formula of binding energy per nucleon, that is BEN. Always remember that. It is the binding energy per nucleon. And as I said to you, in this chapters, modern physics chapters, whether it is atoms, nuclei, dual nature, we are always going to use the unit of energy as electron volts, mega electron volts, that is million electron volts. MeV will become equal to 10 to the power 6 eV, isn't it? And what is the meaning of EV? 1 EV is equal to 1.6 times 10 to the power minus 19 joules. So remember these conversions, because in this chapter we are going to often use these conversions. That is, they will be the energy will be in electron volts and will convert it into joules whenever needed. So this is what I talked in the previous class. Okay. So before I go to the next topics in this chapter, to understand binding energy more closely, I'll give two numericals for you, one or two numericals to you. That will make your binding energy concept more stronger. Okay, shall we take some numerical? I think we can. So, Amruta, you're not going to on your video? If you're hearing me, Amruta. Let me give the question. Give me a second. Yeah. The first question is, calculate the BEN of calcium. Calculate the BEN of calcium. Calculate the BEN of calcium. I hope you know calcium. It is 2040, isn't it? Its atomic number and mass number. So I'm asking you to find what is the BEN of calcium. Some data they have given. Always the questions from binding energy, they will give the data. What they gave? They gave the mass of the calcium nucleus. So mass of this calcium nucleus is given as 39.962589. Remember, in this chapter, you cannot approximate it. I cannot take this as the 40. That's what you want to find. So you want to take all the 6 decimal points. So be very careful about that. This is the observed mass by mass spectroscopy experiment. Okay, this much AMU. Next is mass of neutron. They have given that also. That is 1.008665 AMU. And mass of proton, that is given as 1.007825 AMU. I hope it is clear to you. I gave the mass of each proton. I gave the mass of each neutron. I gave the mass of calcium nucleus by mass spectroscopy experiment. I am expecting you to find the binding energy per nucleon of calcium. If you're understanding this, solve fast. If you are unable to solve, I'll help you. Don't worry about it. But you try solving it. Amrita, you're able to hear me now?
Yes, sir.
Video should be on here.
Okay, sir.
Make it fast, please. I know it's time taking, but we don't have much time, please. Just the multiplication. If you remember the formula, ZMP plus A minus Z into Mn minus M of the nucleus will give you delta M. Then you multiply by C square, you will get the value of binding energy. Divide by A, you will get binding energy per nucleon. Make it fast, please. For your knowledge, in NCERT book also, in the board paper also, they will give you always 1 AMU into MEV. Generally, it is 931, or some books will write 931.5 also. So based upon what the book gives. So if they have given you 1 AMU is 931 MEV, then when you find the mass defect, don't forget to multiply by 931. Then only you will get the value of binding energy in MEV. Never forget that. Any answer? If you are doing calculation properly, you should get the answer. I am not going to appear for the exam. I will use a calculator, but you cannot. Okay, solve by yourself. Any answers? That means you are weak in calculation. So we are finding delta M first, which will be ZMP plus A minus Z into Mn.
Sir,
Yeah.
is it 19.321155?
321155 is the binding energy per nucleon. Is it so?
Oh,
Let us check now. So equal to ZMP. First of all, what is Z in this case? Z will be 20. What will be N? That is A minus Z. A minus Z will also be 20 because number of protons 20, number of neutrons 20. So I'll write 20 times, what is MP? 1.008, sorry, 7007825. If you try to approximate anything, you will not get answer here. Don't forget that. A minus will be once again 20 into 1.008665. And then in this, you have to subtract 39.962589. Let me do it by using calculator. So first I will multiply 20 into 1.007825. 7825. Okay. Plus again 20 into 1.008665. When I do this, I am getting 40.3298. Did you get that? If you got it, you are doing correct calculation.
sir, at the end, instead of subtracting the mass of calcium, we subtracted the mass of neutron.
Okay. Now you see. So we got the value of this expected mass as 40.3298. Okay, we have to subtract in this 39.962589. Let us subtract that. So minus 39.962589. Let me see how much you are getting. If you are doing correct calculations, mass defect should be 0.367211. This is the mass defect. By doing proper multiplication and addition, you will be getting this answer. And then binding energy will become equal to delta M into C square. But I told you, this whatever we get, we are getting in AMU, right? So no need of multiplying by C square here because I told you to convert AMU into MEV directly. So you multiply this value with what? With 931, 0.367211 times 931, you will get the answer in MEVs, isn't it? So we'll do that. Multiplying by 931. What do we get? We get 341.873441. This is the binding energy of the nucleus. And if I want to find what is binding energy per nucleon, which will be binding energy by number of nucleons, how much will be that? If I divide this number by total nucleons is 40, how much you're going to get? 8.546836025. If you are getting around 8.54, your answer is correct. Anybody from any of you have got this answer? 8.54. Check if anybody got the answer.
Sir, I got 8.546.
Enough. If you got 8.546, you are perfectly correct. You'll get full marks. So it is all about addition, multiplication. I hope you understand that there is no much physics involved here. If you are good in calculation, anybody can solve questions from binding energy numericals. But it is definitely time consuming. You can become strong in this only if you are solving multiple questions. Because in exam, you will not have more than 5 minutes for this question. You cannot take 15 minutes for this question. It will be 2 mark or 3 mark only. Because only multiplication and addition, right? Why they will give more marks for this? Take one extra, another question. Make it fast. The next one. You have to find the binding energy per nucleon of chlorine 1735. You have to find it for chlorine 1735. Yes, they have given the values. That is, they have given the mass of proton the same, what I gave in the previous thing, 1.007825 U or AMU, whatever. Mass of neutron is 1.008665 U. And mass of chlorine, that is observed mass of chlorine, was given as 34.980000 U. That is 34.98 only. This is the given data. Now don't take more than 5 minutes. Get me the answer. This time I am expecting answer from you guys. Don't use calculator because in exam calculator will not be there. You have to learn how to solve it fast. No other option. You cannot approximate also. Andrew, I hope you're understanding. Any problem?
No, sir.
Sure?
Yes, sir.
Are you able to get the answers by calculation?
Last time I didn't, sir, but I'll see this time, sir.
Okay, get it. What about you, Mansa? You're understanding what is happening?
Yes, sir.
Okay. Dinesh, you one understanding?
Sir.
Any point of time, if you feel
Yes.
difficulty, ask me. Yeah, it's very basic concept, but important for the examination. So, make it fast, don't take much time. Any answers? So you keep on doing. Parallelly, I will keep on doing my calculator. Just check whether your answer is matching or not. So I'm finding del M first. So once again, what is the value of Z here? 17. What is the value of A minus Z here? 18, isn't it? Protons 17, neutrons 18. So 17 times I will multiply the mass of each proton, that is 1.007825, plus I'll take 18 times mass of each neutron, which will be 1.008665. And I'm going to get the value of expected mass as 35.288995. If you're not getting this, some mistake is there, please check that. Minus 34.98. I'm going to subtract both. That is, in this, I am going to subtract 34.98. 34.98. And I'm going to get 0.308995. Check whether you're getting this answer or not. If you're getting this answer, you're almost done. Then binding
Got the
energy
same
will,
answer.
yeah, good. Binding energy will become equal to, multiply this by 931. So into 931. And you are going to get 287.674345 MeVs. This is the value of binding energy. If I want to find binding energy per nucleon, which will become equal to what binding energy we found divided by total number of nucleons, then I'm going to divide this value with
8.21.
Let us see. So divided by 35, we are going to get 8.219267 MeVs. Check whether you got any answer near this. If you are having any answer near this, then you are right in your calculations. If you are not getting the answer, don't worry much. It's all because of your slow calculation skills, which can anytime be improved by doing many calculations. Again, I'm repeating, this topic that we are learning now is not at all physics much. It is only basic mathematics, isn't it? It is some 6th level, 7th level mathematics. What we are doing, just subtracting, multiplying, adding only. So if you're able to do this, you are fine. If you see both the questions that I have given to you, now let us come back. If you have not got the answer, later you sit and solve it. Now come back to the class, please pay attention now. So if you have not got the, if you are minding the last two questions that I have given to you, that is the question where we found the binding energy per nucleon of calcium, and we found the binding energy per nucleon of chlorine. Both are near 8 point something, right? Now, what is the meaning of this? See, understand, in the previous class I told you, binding energy is the energy which the nucleus is short of to become once again independent. It means in this nucleus, if this energy is not there, that is only stabilizing the nucleus. If this energy would have been there, then the nucleons would have become independent. I hope you're understanding this. Because this energy is not there inside the nucleus is stable. And scientists, by doing experiment in 1900s, 1800s itself, they found that somehow if we are able to release the energy from this nucleus, then we are going to use it for our purpose. Okay? From there only we came to know about nuclear fission and nuclear fusion. Two very interesting topics by which they made bombs. We made atom bombs, isn't it? Atom bomb was dropped on Hiroshima and Nagasaki by America. Remember this? Little boy and fat man, two bombs were there. They both were dropped on Hiroshima and Nagasaki. What were those bombs? They were nuclear fission bombs. And if you think about fusion bombs, that can be more disastrous. It's called a hydrogen bomb. We'll talk about that today. It's not there in the syllabus about bombs, but to make the class interesting, we may talk about that. But let us understand how this fission fusion works. Before going to how the fission and fusion works, you must have one more knowledge. That is about binding energy curve. So next topic that we're going to learn today, give the heading as binding energy curve. Binding energy curve. Sometimes in the board exam, if you see, they are giving directly to draw the binding energy curve. If you see NCERT book, let me go to the books first of all. If I'm able to get the NCERT book, 12th class, which chapter? We are learning physics. In physics, we are in physics part 2. And here, nuclei chapter, 5th chapter, that is 13th chapter. So I hope everybody is able to see the book. And in this book, I am focusing on this particular graph. Yes. This graph sometimes is asked in the board examination to be drawn by you. 2 mark. Just to draw this graph as neatly possible. That is as much better as possible. You are sometimes expected to draw this graph. I hope everybody is able to see it. If not, open your book near you and check it. If you're able to see the board, it is well and good. Now pay attention. Let us spend 5 minutes time to understand this graph properly. So here what the graph has been drawn? The graph has been drawn between binding energy per nucleon, like how we found for chlorine and calcium, right? Like that, they found the binding energy per nucleon for all the elements on the periodic table. And they are plotting against the mass number. So when a mass number is 0, 25, 50, for everything. So in this graph, all the elements are coming and some elements they have listed. Not all the elements are listed here. Few, some 10 elements are listed here on the chart also. So if you see, this is isotope of hydrogen. If you see clearly, it's not hydrogen alone. It is deuterium, tritium, helium, lithium, nitrogen, oxygen isotope, carbon, sulfur, iron, something, indium, obidium, whatever name it may be. W is what? Tungsten. I don't know much about chemistry. W, whatever. AN. And U is uranium. That I know. So like that, these elements, what is given here? Binding energy per nucleon. By now, you should have understood, if you have understood the concept of binding energy, the bigger the binding energy is, the greater is to break that nucleus, isn't it? If binding energy is bigger, it means more energy is required to disintegrate it. If binding energy is smaller, less energy is required to disintegrate it. Now, if you see here, you will realize that most of the elements show a great stability. That is, approximately, I will say, from 30, see here oxygen around from 30 to 200, actually 170 to be exactly, 30 to 170, the value of BN is above 8. Are you able to feel that? 0, 25, 50, somewhere here 30 will come, where the graph became above 8, and here it is going below 8, so around 170. So what we observed that most of the elements, that is mass number lying between 30 to 170, are showing good stability because their BN is more than 8. Only few elements which have mass number above 170 or mass number below 30, they are having little less binding energy. Are you getting my point? So if you see all these elements, they are having great stability. They are very stable nucleus. And if you see beyond this, it is reducing, becoming less. And if you go before 30, once again reducing. That too, deuterium and tritium is having very less binding energy. That's why they are very highly unstable. You will not find easily deuterium and tritium. In last class also I told this to you. In last class also I told, in our nature, we have abundancy of protium, but deuterium and tritium are not abundant because they're not stable. Their binding energy is too low to be stable. The nucleus always breaks. It does not remain itself. So it's difficult to find deuterium, tritium in nature. Okay. So this graph, I hope you're clear in the graph, what they're saying in the graph. The graph is being plotted between binding energy per nucleon of various elements versus its mass number. Now, very crucial thing I'm going to speak. Pay attention, Varshita Shri, please, okay, here on the class for coming 10 minutes. Okay. So now everybody pay attention. We came to know that most of the elements are having binding energy in the range of above 8, they are stable. Few elements having less than 8, around 7.3, 7.5. Some elements are having, once again, 7.6, 4, even 2, or less than 2 also. Somehow, pay attention, somehow, if you are able to convert a low BEN nucleus into a high BEN nucleus, how will you do that, first of all? If there is a low BEN nucleus, what is the meaning of low BEN nucleus? Low BEN nucleus means it has less binding energy. If you are going to convert it into a high binding energy nucleus, how is it possible? By taking out some more energy from it? Some of you will confuse here now. You will think adding only will increase the binding energy. No. Binding energy is not by adding. Binding energy itself is defined as what energy the nucleus is short of to become independent. So if you see iron has the maximum stability. Iron is the most stable element in the periodic table, which has the highest binding energy, 8.75. See here written also. 8.75 is highest for iron. So if you compare iron and uranium, uranium has less binding energy. It means it needs less energy to become independent. Iron has more binding energy. It means it needs more energy to become independent. If I want to convert uranium into some iron or something here, then how I'll do? I have to take out more energy from it. Initially, it was 7.5 short of. I want to make it 8.5 short of. I should remove one more energy to make it 8.5 short of. Are you getting what I'm trying to say? So if you are converting a low BEN nucleus into high BEN nucleus, there will be an energy release. Very crucial thing I told. How much I understood, I don't know. But I'll make you understand. That is, if we are converting a low BEN, BEN means binding energy per nucleon nucleus, into a high BEN nucleus, then you are going to have energy release. Do you understand this fact? Why I am saying energy release when converting from low BEN to high BEN? Because one element is having low BEN, means suppose it is having here 2.5 tritium. Suppose it is 2.5. I want to make the binding energy 6. How can I make its binding energy per nucleon 6? If I remove additional 3.5, isn't it? It had its BN is 2.5, means it is 2.5 MeV short of to become independent. If I am going to make it BN 6, how I can make it BN 6? Not by adding energy in that, by removing 3.5 more energy from it, isn't it? If I remove 3.5 energy more from it, it will become BN 6 nuclei. And that happens, this energy is getting released, no? That only we are using as fission or fusion. Is it clear to you? Fission means if you are breaking a high BEN nucleus, that like uranium or plutonium or thorium, into two mid-sized nucleus, because mid-sized nucleus will have high BEN, some energy will release. That energy is called as fission. Or see here, deuterium, tritium, these kind of low BEN nucleus, if you are combining to make helium, once again I am converting low BEN to high BEN, I will have release of energy. That is called as fusion. So what is fusion? Fusion is combination of light nuclei of low BEN into a high BEN nucleus. We will definitely have energy release. I told you before sometime. Fission is breaking off a low BEN nucleus into mid-sized nuclei which are having high BEN. Once again, low BEN to high BEN, energy will be released. So from here to here, if you are going, it will be fission. From here to here, if you are coming, it will be fusion. Is it clear to you what is the difference between fission and fusion? In fission, we are going to break. See, many of you may know this, but not technically. You may know fission means breaking, fusion means combining. But what is breaking? Heavy nucleus is breaking, because heavy nucleus has low BEN. If that nucleus becomes too mid-sized nucleus, then what happens? It releases some energy. Same way, if a light nuclei, which has low BEN, is converting into a high BEN nucleus, we will once again have energy release. So if two hydrogen is combining, deuterium combining to become helium, you may have big energy release. And that energy release is only called as nuclear fusion reaction. Is it clear to you? So the same thing has been given in these two paragraphs. If you see this in these two paragraphs, if you read, you will realize a very heavy nucleus has lower binding energy per nucleon. Thus, if A240 breaks into two 120 nuclei, nucleon gets more tightly bound. This implies energy would be released in the process. It has very important implications for energy production through fission. Same way, consider two very light nuclei joining to form a heavier nucleus. Binding energy per nucleon of fused heavier nuclei is more than binding energy per nucleon of lighter nuclei. This means the final system is more tightly bound than the initial system. Again, energy would be released in such process, and that is called as fusion. I hope you are getting some clarity over what is the difference between fission and fusion. In the case of fission, we will break a heavy nuclei into mid-sized nuclei. In fusion, we will combine light nuclei to form comparatively heavier nucleus, which has higher binding energy. If you have any doubt, anybody, unmute yourself, ask me, I'll make it clear. If there is no doubt, I'll move further. If any student has any doubt in this, whatever I spoke now, you can unmute yourself and ask me. Otherwise, I will take it as you have understood this. I'll proceed further. Everybody is clear in this? Andrew, you understood?
Yes, sir. Understood.
Amruta, what about you? Not in the class properly today, on the camera. Understood or not?
Yes, sir.
Varshita Shri, what about you? Understood?
Yes, sir.
Ananya, got it? I hope you have got it.
Yes, sir.
Yeah. So now if I go in a little bit more detail about fission and fusion, see here how the questions will come in the board exam. I'll tell you. You are supposed to remember these three reactions. One more thing I'll tell you, interesting thing only. Uranium has two drawbacks. One thing, it's low BEN. Second thing, it's heavy size. Since it is having heavy size, nuclear force is also low there. I told you nuclear force is very short range force. Since uranium has 235 elements, that are not elements, members, that is nucleons. If it has 235 nucleons, then you can understand that its size will be very big. If it is big sized nuclei, the nuclear force will become less because range will become big. And when the nuclear force becomes less, it is highly unstable. If it is unstable nucleus, already it is unstable, you go and throw one more nucleus on it. Nucleus means neutron on it. What will happen? Already it was unstable, about to break. You are throwing one more neutron, it will become further bigger, it will disintegrate. If it disintegrates, it has three possibilities. One possibility is breaking into barium and krypton, releasing 3 neutrons. If you ask me how 3 neutrons, conservation of mass. If it is 144, 89, what is missing is 1. So 3, I mean. So 3 times 3 neutrons will come out. Are you getting my point? How 3 neutrons came? To conserve the mass, we are writing the equation. Same way, second possibility is it may become antimony and niobium, or it may become xenon and strontium. Difference is, in all these three cases, number of neutrons coming out will be different. Like in one case, 3 neutrons came. In one case, 4 neutrons came. In one case, 2 neutrons came. Now, I had nucleus. I bombarded one neutron. Neutron made the nucleus unstable because of increasing the distance between all more nucleons and making it more unstable. It broke. But after breaking, it released 3 neutrons, right? These 3 neutrons will once again go and hit other uranium. You don't think that if you have 1 million uranium atoms, I need 1 million neutrons. One neutron is enough to break all 1 million uranium atoms. Are you getting why? Because one neutron will go and hit one uranium, creating either 3 or 4 or at least 2 neutrons. Now, these 2 neutrons will further go and hit other uranium. Once again, 2 may come out. Once again, the 2 may go and hit another 2. Like that will become a chain reaction. And if this chain reaction is uncontrolled, we make atomic bomb, atom bomb. So in atom bomb, what we do? We do uncontrolled nuclear fission reaction. That is, we make a chamber. In that chamber, we put uranium element. Element means it will have millions of atoms of uranium. And we take one neutron, bombard it. So when it is falling down, like, have you seen the videos how they dropped it? They took from a jet and they dropped from top. When they are dropping the head, they will call it as nuclear head. When they dropped that atom bomb, little boy and fat man, what was happening inside? The neutron is released. Neutron will go and hit the uranium. Moment it hits, chain reaction starts. Energy keep on getting released until the full uranium, all the 20, 100, 200 million atoms of uranium are fully broken. Energy will keep on releasing. And you see, they have explained how the energy releases also. If you realize, you will understand here how the energy is released. So energy is released because binding energy is different in the product reactant side. Binding energy is different in the product side. Subtracting those, you will get. So approximately for each nucleon, there will be, for each nucleus, there will be a 216 MeV released. One nucleus. If you have 1 million nucleus, this multiplied by 1 million MeV energy released. Are you able to understand that? So how much energy is going to get released? It's going to be huge. And that's how we make fission reactions. Same fission reaction, if it is controlled fission reaction, that is also possible. How? 2 neutrons came out. 1 neutron somehow you control by using lead bricks. Only 1 neutron is allowed to go. Then you get controlled fission reaction. That's how we make nuclear reactors. Yes, like you go to Kalpakam near Mahabalipuram. We have nuclear power plant. There we are doing same reaction, but controlled nuclear reaction. That's why some people are fearing about nuclear reactors. They think if we are not able to control it, what will happen? Like Chernobyl. Chernobyl became uncontrolled nuclear fission reaction. It will become bomb. But if you are properly controlling it, then there is no problem. So all the nuclear power plants, in Tamil Nadu we have 2. One in Kalpakam, one in Kodunkulam. Both are having same fission reaction inside. Second thing is fusion. What happens in fusion? As I said you, here we will have combination of hydrogen into helium. Or maybe protium becoming deuterium, deuterium becoming helium. Like that reactions will be there. And you see, you will realize that this case will have more energy release. See here, for each nucleon, we had 0.9. For each nucleus, we have 216. But each per nucleon, how much released? Per nucleon, only 0.9 MeV is released. Very less only. But here, per nucleon, we can have even 4 MeV energy released. Why? Because here you see, the difference between uranium and mid size is very less. 7.5, 8.5. Only 1 MeV can release. But here you see, if it is 1 to 6, 1.5 to 5.5, almost 4 MeVs per nucleon can be released by fusion reaction. That's why fusion reaction is more effective. And fusion reaction has no byproducts. If you see fission reaction, we are getting barium, krypton, antimony, niobium, strontium, xenon. They are again radioactive. It is problem for decomposing that. Actually it is a nuclear waste we are dumping in the ocean today. Wrong. But if you are able to make energy by fusion, we are going to have no byproduct. Only hydrogen is coming out, helium is coming out, gas only. No problem. So basically, nuclear fusion reaction is called as clean energy resource. Problem is there in that also. That fusion reaction is difficult to conduct. Why difficult to conduct? Because in fusion reaction, we have to combine hydrogen, right? Hydrogen highly positive, hydrogen highly positive. Positive, when you're bringing close, they will have strong repulsive force. And we have to overcome this proton repulsion barrier. If you are able to overcome this proton repulsion barrier, only then your fusion reaction can be conducted. Are you getting my point? And to overcome that, what we need? We need very high temperatures, very, very high temperatures. That is again a tension. So basically, nuclear fusion reaction takes place along with fission reaction. So tomorrow, if you are able to have any hydrogen bomb, nobody has used till now. They have made. Many countries have a hydrogen bomb. Hydrogen bomb will have a fission chamber also, fusion chamber also. First, fission chamber will create energy, and that heat will be used to overcome the proton repulsion barrier. And when it fuses, it will further release energy. So when some country drops hydrogen bomb, like if Russia drops on Ukraine, suppose, in that case, the disaster will be huge because it will be fission plus fusion. Fusion cannot happen independently. Imagine when fission alone happened in Hiroshima and Nagasaki, when little boy and fat man was dropped, so much destruction happened. Till today, we have impact of it. If somebody drops hydrogen bomb, imagine what will happen. It will be disaster because we will have, it will drop, huge wave will come out, and few seconds, one more wave will come out. It will be disastrous. The whole country can be wiped out. Yes, instant vaporization, as you are saying, Pratap. So whatever I spoke now, it is given here also about why it is difficult, proton repulsion barrier. So we need how much energy? You see, they told for conducting fusion reaction, we need 3 × 10⁹ kelvins. 3 and 9 zeros, that much Kelvin of heat energy you need, temperature you need. Then only you can have fusion reaction. And that is difficult. That's why till today, so much technology has come. Till 2025, we don't have a single nuclear fusion power plant. Even America or Europe are not having. We have fusion power plants. Many we have. India itself, we have so many nuclear fusion power plants. But we still don't have fusion power plants, because fusion power plants are one second, guys. Yeah, this is for your room and this is for the inside room. Yeah. So guys, let me wind off today's class. Many people are waiting